perception, decision, execution. It's the way fighter pilots teach maneuvering to younger folks. Did you see the right thing? Based on what you saw, did you make the right decision? And then based on your decision, did you physically execute it correctly? Trying to wrap all that up and just hit the I believe button on artificial intelligence, I think, is the wrong path. Building systems that are modular, hybrid, and hierarchical from the start, and built in such a way that you can address the ultimate questions that a certification authority are going to ask you. I think that's the absolute best practice.
Welcome to The Vertical Space, the podcast at the intersection of technology and flight, featuring deep dives with innovators, early adopters, and industry leaders. We are your hosts, Jim Barry from Celerity 05 and Peter Shannon and Luka Tomjanovic from Radius Capital. At Celerity 05, we believe that breakthrough air transportation capabilities come from leveraging current and emerging technologies, and that companies achieve profitability through relevant technologies, strong teams, and a deep understanding of the aviation market. Connect with global aviation experts at celerity05.com for feedback and recommendations to chart your path to success. At Radius Capital, we invest in early-stage deep tech that redefines what is possible in aerospace. We partner with founders building next-generation aerospace capabilities, from advanced design and development tools to the digital transformation of the flight environment, novel use cases and forms of flight, and the software and systems that make them possible. If this describes you, reach out. We're excited to connect. All right, let's dive in.
Hey, welcome back to The Vertical Space and our conversation with Chris Gentile, General Manager, Tactical Autonomy at Merlin. Chris is an impressive person, as you'll see. And frankly, you feel a little bit better about our American military and industry when you hear a serious, bright person who served in our military and is now doing important work in the industry. With some of the pomp, superficial, and unfocused work in our world and in parts of our industry today, it's frankly good to hear non-hyped, serious competency from a person who is focusing on meaningful problems that have to be addressed for our commercial and military requirements. We start a conversation around autonomy, and I really like Chris's comments around focusing where value can be added and how we have to start with baby steps towards continuous improvement. He discusses how and why he started with autonomy, cool story, and how his autonomy focus started with defense applications. His answer of why he focused on autonomy is in and of itself a terrific discussion. We then discuss the major milestones towards trusted autonomy and listen to his explanation of how autonomy is a tool to open up a whole new trade space that gets back to quantity mattering. And as he says that, in his mind, this is the clearest path to continuing to deter global conflict and allowing the world to continue on this path to greater prosperity. Good discussion on air dominance, what we've experienced in recent decades, and how it's dramatically different today and how it's going to be in the future. He then discusses the future of autonomy in the military and the significant changes the military will face in the near and long term. He answers Luca's questions on what's needed to develop an autonomous system, from collecting data, training, and developing algorithms, testing and operationalizing them, and the processes and the challenges along the way. Towards the end, Chris discusses the recently awarded Air Force's Next Generation Air Dominance program, which you'll hear was awarded just before our recording. Cool to hear a fighter pilot's perspective on this new weapon system. By way of background, as mentioned, Chris is the General Manager, Tactical Autonomy at Merlin, and previously was an F-15 and F-22 fighter pilot with the United States Air Force. He is a graduate of the United States Air Force Academy with a bachelor's degree in astronautical engineering. A substantive, serious, meaningful discussion. Thanks very much, Chris. And to our guests, we hope you enjoy our discussion with Chris Gentile as you focus on important problems to solve while operating profitably in the vertical space.
This episode of the Vertical Space podcast is brought to you by UAvionics. UAvionics is the leader in low size, weight, and power certified avionics for manned, unmanned, and advanced air mobility aircraft. Let UAvionics help you achieve your goals, whether that be type certification, airspace access, or beyond visual line of sight operations. UAvionics has certified and certifiable communications, navigation, and surveillance avionics for your aircraft. So head over to uavionics.com or Google it to see how you can start flying safer and move your platform forward into shared airspace. Chris, welcome to the Vertical Space.
Hey, thanks for having me. Good to be here.
So we start by asking if there's anything that few in the industry agree with you on.
First off, that's a bold statement. I don't know what everybody else thinks privately, but the biggest thing that I tend to foot stomp, having been in the space for a few years now, is that I'm not sure I agree that autonomy itself is a product. I think autonomy is a tool. It's part of the evolution of aerospace technology that goes back to the dawn of these systems. And the real product that comes out of that is what new mission can I do? What cost efficiency can I gain? In the defense space, what increase in survivability or effect can I take? But autonomy itself is not a product. I don't know of any customer out there that's going, I'd like to buy one autonomy, please. The trick is in tailoring all the advances in artificial intelligence, autonomy, automation, et cetera, and turning those into meaningful user stories, whether that's for defense community, civil community, an emerging market, et cetera. But I see a lot of folks who say they're autonomy companies, but it's not immediately clear what their actual product, what their actual value is. And I think that's something we're going to see a lot more clarity on as we move past this first wave of excitement and into delivering real capabilities.
Okay, not to stretch the analogy, but if autonomy is a tool, there are tool companies. So
Yeah,
why wouldn't there be an autonomy company that's building autonomy as a tool?
I think that's reasonable. And I think that's the direction that you're starting to see, a lot of the more mature players take on, realize, what aspects of the stack are you going to specialize in? Just as there's different variations of tool. If you look at what it takes to create, modern semiconductors, there's a global supply chain just to get to machines that enable that, whether it's sitting in Taiwan or, being built here under the CHIPS Act. And I think you're seeing, at least in my corner of the world, the software autonomy space focused on aviation, you're seeing different groups start to specialize on different areas there, all the way from just modernized flight controls, taking on the mantle of stuff that have been under avionics and autopilot companies for decades, all the way up to the very high end of human interaction, command and control, et cetera.
What are the implications for companies who are thinking about autonomy as a product as opposed to a tool?
I think that presupposes a lot of opinions about how any individual customer will choose to procure this. Much bigger names, whether it's your Palantirs, Andurils, et cetera, have been talking for a while about shifting the DoD specifically towards a more modern software acquisition approach, license-based sales, more commercial applications, things like that. And I think that's a good conversation trending in the right direction. But the fact remains that the vast majority of our defense budget is still spent on platform centric capabilities. And so if you want to sell these sort of software tools, you need to have some sort of close coupling with the airplane or the box that it's going to go on. And so I think that's the first hurdle, that a company needs to decide is to what degree of exclusivity are you willing to accept? What degree of specific tailoring of your tools are you willing to accept? In what ways are you going to trade away potential larger market in the long run for immediate deployment, buying down some of the risk towards immediate platforms right now? So I think that's the first big question. The second is, companies should just be realistic about which parts of the stack their talents are in. Modern aviation, civil, military, emerging mobility markets, things like that. These are some of the most complicated machines humans have ever built. The idea that an early stage startup is going to come out and be able to revolutionize every aspect of it, but somewhat unrealistic. And so identifying where the specific value can be added, which network of partners, both traditionals and other emerging peers need to come together in order to solve these problems. There are a lot of conversations happening about this. I'm not sure that anybody has all the answers. That's for certain.
Chris, we had a guest on a couple of episodes ago who said one of the mistakes some of the US based companies have is they're focused more on capability rather than the customer experience. And you're saying something similar with your response of stop focusing on autonomy, think about what the value of autonomy is going to bring to the space. How is the customer experience going to change through the introduction of autonomy? And how is it different than how most people are thinking today?
I've had a couple different versions of this conversation, and I almost always reference a really incredible treatment of this topic. There's a book called Tiger Check. It's by a guy named Stephen Fino. His call sign's Munch. He's a former F-15 pilot, got his doctorate at Johns Hopkins. He works at Raytheon now. But it describes the introduction of automation into fighter aviation going back to World War II up through like the F-15. One of my big takeaways from that book is that the fighter community and guys who fly fighter aircraft certainly have a lot of opinions, but there's almost this incredible horizon singularity that every piece of technology and tactic that occurred before now is an immutable law of the universe and the God-given foundation that everything we do is built on. And everything in the future is kind of BS. I'm just going to white knuckle it, be a knight of the sky and go from there. And so where that leads to is the idea that a lot of these technologies we're talking about, there's two key things that frame my thinking on it. The first is that we're talking about evolutionary, not necessarily revolutionary tools, but that evolutionary improvement in tools can lead to revolutionary changes in outcomes. So that's the first. There have to be baby steps. We can't ask an entire community whether they're charged with moving millions of people a day safely around the world and civil applications, whether they're charged with projecting power, defending the nation on the military applications. They can't just hit pause on all that and come out a year later with a completely different construct, right? We have to take steps along the way. And the second major aspect to this is that to actually use these tools to generate those user experiences and change capabilities, there's a technical problem, which a lot of people and a lot of money are focusing on, and there's equally a cultural problem. If you want to look at aviation autonomy, one of the key fielded systems right now is called automatic ground collision avoidance. It's deployed on F-16, F-22. I think it's coming out on F-35 and a few other platforms. And if you've seen Top Gun Maverick, when they pass out due to the G forces, the airplane almost hits the ground. Great scene. This system basically stops that, right? In the F-16, if it detects that the aircraft's potentially going to impact the ground, requires more than about a 5G recovery, which is pretty aggressive. Unless the pilot actively disengages it, the system will take over, recover the aircraft, avoid the ground, return it to safe flight, and then return control to the pilot. That was roughly mature in the early 90s. There was a joint Air Force NASA program that demonstrated that on F-16s. We didn't field it until 2014. In the time between the final demonstration of that NASA program and the fielding of it in the operational fleet, we lost 47 aircraft and 51 people. Not because the technology wasn't ready, but because the culture wasn't ready to accept this loss of control for operators. They prioritized weapon upgrades over the safety upgrade, et cetera. And so, as you go through that, I think that focus on the user experience, on the specific benefit, being able to coach it in terms that meet the people who are entrusted with, buying, maintaining, or operating these systems where they are, is the real differentiator. And companies that can solve that cultural fit along with their technical product are the ones that are going to be successful.
And also, I think there's a difference in who the customer is. Back to Jim's question, what the perception of value is, it really is different from a defense application and a commercial application. In the commercial world, there's a cynical view of saying, well, really, what do you get out of replacing the pilot? You invest a lot of money to get something that is as good as a pilot, ultimately. And so it's a longer conversation that we can get into in the course of this discussion. But maybe before that, how did you get started working on autonomous systems?
Literally, I stumbled into it a little bit. So I had a background in aviation engineering. I flew fighters in the Air Force. I did some test work, got exposed to a couple other pieces of advanced technology, and then I was looking for something to do when I retired. And I bumped into a company that was getting ready to attempt to compete in the DARPA Alpha Dogfight program. And I'm sure we'll talk about that over this podcast. But that was fundamentally trying to take a very narrow application of autonomy using a combat use case, one that gets people's attention, and just see where the state of the art back around, 2019, 2020 was. And I signed a 20-hour consulting contract with a 5-person company to basically try to teach a couple of programmers a little bit about dogfighting. I get 2 or 3 hours into that contract right after I retired, and I think I said something like, I know just a little bit of Python. Let me show you what I'm talking about. And from there, it was off to the races. That was an exceptional time in the industry, specifically from a defense application, because 3 major forces came together. The first was that the nation got serious about the need for autonomy. And I'm sure we could talk about this more, but we're in a world, in the defense world, where quantity matters. You see this in Ukraine. There are thousands of various sized drones flying over that battlefield every minute of the day. The second was that certain tools finally matured enough to allow, as Steve had started talking about this, right? That was a few years into the modern AI revolution. NVIDIA was starting to crank out, the tools and the infrastructure we used to build these systems. So we had a need come out. We had tools that were showing promise in meeting the need. And then the last thing, again, specifically on defense, there was a realization that maybe the kind of people who know how to bend metal and build airplanes are not necessarily the same people who know how to write this level of software. And so the government made steps to open up industry to more diverse participants. And all three of those things came together and I think really lead to where we are now and certainly my place in it.
Interesting. So looking back those several years, what do you see as some of the big milestones and inflection points in driving towards trusted autonomy?
Yeah, a couple of major milestones. The first big one is that even though it's still limited and there's more room to go, the Air Force has gone out and explicitly deployed some of these technologies on the Vista F-16. The Secretary of the Air Force himself went and flew on an airplane that for at least part of that mission was controlled by a couple of different AI agents. So that was the first one, and just showing that it could actually, in a small way, still a lot of work left to be done, start to make that jump from research, simulation, video games, if you will, out to the real world. The first time, even in training with all the rules around it, that a human who was fighting their best fight got gunned by an autonomous agent was a pretty big deal. The second thing that you just can't ignore is, what we've seen in Ukraine. This combination of computer science, artificial intelligence, expedient manufacturing, things like 3D printing, stuff like that, and the scale that we're able to bring means that, $200 drones can take out multi-million dollar legacy weapon systems. And while there are challenges in extending that to other theaters, across the Pacific, et cetera, I think it's certainly gotten everybody's attention. And, I'm just following a lot of the messages here. Alex Karp's book just came out a few months ago and hits these points better than I ever could. So I think those are the two big things, is that we showed that these could move beyond the lab, at least in limited fashion. And in Europe, we see very much the need for them.
And I'm really excited to ask you this follow-up question because you've seen state of the art on both sides, being deeply entrenched in the Air Force and working on some of these systems, but also in the industry. And so what really honestly is the gap between what has been demonstrated at some, small scale or in the lab or some limited technical demonstrations versus what is required and what needs to be deployed in real world operations? So I guess two questions, what is that gap and what really is the state of the art?
Oh man, there's a bunch of things to get at there. The first gap is that you could sum it all up and say certification, right? There's a lot of reasons that autonomy is hard. There's trust, explainability, performance, transition to aircraft, all those things. But at the end of the day, achieving a civil certification or military airworthiness on these capabilities is the bar that needs to be crossed, and that has not fully and comprehensively been crossed yet. And so, you've got companies out there that are addressing different parts of that, but that's going to be the single biggest one. Now, realize you said earlier, like customers have different opinions, different requirements, different levels of acceptance of this. I think you very much see that. In Ukraine, their standard is like pretty much will it go that way before it fails? That's good enough for them to put into practice. For the U.S. Defense Department, there's a balance: threat to life, threat to risk, ability to project power. If you're talking about a civil application, despite obviously a very tragic year so far, Western large airline transport is the safest and most effective complex system humans have ever built. And to meaningfully improve on that is going to take a very high bar of proving your technology, proving your certifications before you're allowed to potentially impact that. But it all comes back to the same thing: is can you demonstrate using formal systems engineering and certification processes that you've met that bar for that domain?
So how is that achieved? How can an entity, an organization, whether this is a startup or an incumbent, go in front of the FAA and say that their autonomy stack is safe enough? What are the best approaches? What are the best practices?
I think there's a couple different people doing a couple different approaches. What I believe is that the core of this has to be designed in from the start. If you look at the current progress on some of the large language models, your GPTs and things like that, I'm going to simplify a little bit, but you're seeing kind of the same process repeated over and over again with each new model that gets released. And that they do a bunch of training, they do a very automatic process, right? The once the algorithmic challenges are solved, it's fundamentally like, do you have enough data and do you have enough electricity, and something comes out. And then people start to find all the challenges with it. There are hallucinations. It's, going off the rails in one way or another. And then there's a lot of follow-on fixes that go into it. Do I add filters for topics that I don't want it to be able to say? Do I force it to fact check certain things? Do I literally make GPT call itself before it outputs its thing and, go use other agentic features to search the web and make sure that those legal citations actually exist before some lawyer, shows up with a brief with a bunch of fake cases? I think there's some folks who thought that that sort of model would work in the autonomy space as well, that, you have some shiny new tool. A couple of years ago, it was reinforcement learning. Maybe now it's VLMs or something that's going to get me like 90, maybe 99% of the way. I'm going to be able to demonstrate very impressive demos very quickly. They're going to work great in simulation. They're going to work great in constrained environments. And then I'll just, knock down some of those, outstanding areas with a little bit of post-processing. I think that method is fundamentally flawed for a bunch of reasons, but I think that all of these features have to be addressed. All these requirements have to be addressed up front in the design. Are you architecting the system in such a way that you can explicitly get the trust and explainability from each step along the way? If you wanted to use like the self-driving car industry as an example, in general, most of these systems work that they use, cameras, lidars, and other sensors to perceive the world, and they build a map of the world. And, even if it's not exposed to an ultimate consumer, to an engineer, they're able to look at that map of the world, picture of the world, and immediately diagnose, it didn't see that bicycle, or it addressed something incorrect. And from there, what trajectory do you want to build for the platform to do? Okay, does that trajectory make sense? Can I check that there? Then, okay, am I able to effectively guide this vehicle or this airplane across that trajectory? Things like that. Perception, decision, execution, right? It's the way fighter pilots teach maneuvering to younger folks. Did you see the right thing? Based on what you saw, did you make the right decision? And then based on your decision, did you physically execute it correctly? Trying to wrap all that up and just hit the I believe button on artificial intelligence, I think is the wrong path. Building systems that are modular, hybrid, and hierarchical from the start, and built in such a way that you can address the ultimate questions that a certification authority are going to ask you. I think that's the absolute best practice as you go forward there.
I think I'm grappling with a couple of questions in this topic area that I'm trying to sort out. One of them is, what use cases demand this highest level of autonomous behavior, this very dynamic, reactive type of behavior? And then in what domain areas or flying on what type of a platform are the iterations going to happen the fastest in the development, such that on that platform, the technology leads the rest of the industry? Secondary to those questions is this FAA question of, if you do bring it into a certification regime, how would you do it and for what purpose? The why. But the first two questions are the ones that are hanging in the back of my head as we sort of survey this here.
Absolutely, man. Those are great questions. I think it's especially interesting because I guess I've been thinking about it a little bit differently, which is that, in the long run, the highest level of autonomous behavior has applications across all these things, right? Like in general, whatever the field is, civil, military, airplanes, cars, whatever, like we're trying to achieve a superhuman level of performance and open up some new suite of capabilities and missions. If that's urban mobility, we want to give people hours of their lives back at higher safety, lower cost, improved efficiency to what they get now. If it's in the defense application, we want to be able to, project power, hold adversaries at risk, defend forces at a higher level than we are now. But I go back to what I said earlier, that evolutionary step. The immediate applications are, if I'm looking at a small drone platform like Ukraine, am I able to maintain awareness or hold targets at risk at a greater ratio than the number of humans I have? So instead of one human looking through one camera or one human flying one FPV drone and holding one target at risk, can I start to apply autonomy to increase that ratio? I think it's the same thing on some larger platforms like the United States' Collaborative Combat Aircraft Effort, CCA. Hey, there is value in just providing an additional sensor or an additional weapon that doesn't have to be physically attached to an F-35. If the first realm of these aircraft did nothing more than fly in formation and augment the sensor weapons capabilities of a formation of F-35s, that's not an especially complex AI task. There are all these other challenges in autonomy of just how you make that airplane work reliably and effectively and at meaningful workload. Now, in all these cases, there's a long run, right? In Ukraine, and you're starting to see some of this development occur. Our dozens to hundreds to eventually thousands of these platforms able to distribute sensing perception amongst themselves, make targeting decisions, and prosecute complex engagements. On the CCA side, are these going to generate what we've seen in science fiction, books like Ghost Fleet and stuff, where they're able to execute superhuman performance and continue to reduce that workload? I think each of those cases, as far as which platform is going to lead, I think they're all going to push different aspects of that envelope in different directions. I think smaller, like group 2 and group 3 platforms are going to push the boundaries in collaborative perception, sensor fusion, heterogeneous teaming. So taking non-similar platforms and putting them together so that you can get more than the sum of the parts. I think that's where you're going to see those capabilities really exceed. On larger efforts like collaborative combat aircraft, I think that's where you're going to see new frontiers of decision making, really, able to infer aspects of the battle space, take advantage of it at a slightly more individual level, maybe using things that weren't obvious to humans, start generating superhuman performance there. And on the civil and other side, I think you'll start to push the bounds of network effects of efficiency, right? How much can I optimize the fuel burn of a large aircraft, the fleet deployment of eVTOL, urban air mobility systems, in order to effectively serve their population while minimizing noise pollution, carbon footprint, et cetera, things like that. And so I'm not sure there's a one-size-fits-all answer. I think you're going to see different parts of the industry solve different parts of the problem. And ideally, if we go back to, again, that modular, hybrid, and hierarchical approach, then we'll be able to transfer some of these behaviors and technologies across these domains and realize additional benefits there.
Do you think it's an important distinction, as you describe these different uses of autonomy, to distinguish between autonomy that is powered by deterministic code versus autonomy that is powered by some flavor of AI that is so dynamic that it is not deterministic? So at the first extreme, it could be, yes, we can put large numbers of drones in the air with small numbers of humans operating them, and create so-called swarms and direct them at lots of targets. But we can do that ostensibly just by flying lots and lots of waypoints. Those aircraft themselves are not operating at the type of autonomy level that you would see in something like a dogfight. At the other end of the extreme, we see drones that are being intercepted by other drones, and it would be wonderful if they could make evasive maneuvers and have much more dynamic behavior. That, to me, seems like a different software architecture in order to enable that level. And as you talk about this, it feels like you're bridging across a lot of different behavior types. How do you think about that distinction? And is it important? Is it something that we need to surface here?
I think it's absolutely important. My personal view of the industry is that, at least in defense, aircraft autonomy, you've really got those two schools of thought. Right. You've got companies or researchers who are growing out of like the surveillance missions, think Predators and Global Hawks and things like that, who very much think of autonomy as the ability to automatically build a plan and then adjust that plan, that flight path, when something in the environment changes. But there's kind of always a plan. If any of our listeners are civil pilots, especially like commercial pilots, there's always a full flight plan in your FMS and your autopilot system. And the computer is just jumping in and changing aspects of that. And then you've got the kind of companies who cut their teeth on DARPA Alpha Dogfight and Air Combat Evolution, which were heavily using reinforcement learning and things like that. And they think about problem space very differently. I could say that the team that I was working with, there was no path that existed more than about a second in the future, right? That was constantly, reacting to the information that it was given and going forward from there. That said, I do want to foot stomp something, and I think the DARPA team who led this program would say the same. We all think that dogfighting is, the ultimate application of this. It's the most dynamic. It needs the most AI. 1 versus 1 dogfighting against a similar opponent, especially when you have good data on what they're doing, that's absolutely a solvable math problem. That doesn't necessarily need AI. We chose to use AI because we were interested in exploring some of the boundaries of that, especially in the case where we could go back and verify, either ahead of time or after the fact, like what the optimum solution was and how close we were able to get to it with the hardware and algorithms that we had available to us. So I think the winners in this space, and I don't mean that from just a company that's going to succeed, right? Like the US government is sponsoring the creation of reference architectures in ensuring that you can bring together these different types of technology, that when the problem is solvable deterministically or has a high safety impact, you're able to use those tools when the problem is not tractable, or the performance of using, those traditional techniques is not enough, that you have an architecture that allows you to introduce some of these advanced capabilities, take advantage of the hundreds of billions of dollars of research that's going into AI right now, but do it in such a way that's bounded because of the domain, because of the risks of failure. It's not like we laugh at what GPT, hallucinated. It's an airplane crashes or the wrong target gets hit. So can we build the right safety bounds, tools like runtime assurance, which are defined standard, like those words mean things to systems engineers, that as we introduce those complex functionality on one end, we're building the right system architecture under it that can say, okay, how will I know if it's wrong? What do I do if it's wrong? And can I achieve at least a fail-safe backup using techniques that I can traditionally prove and certify?
Chris, when you came out of the Air Force, you said that's when you got excited about autonomy, and you said, this is going to be my area of focus. What was the problem that you thought could be fixed from autonomy that gave you the most energy as you came out of the Air Force? What did you say, I've got to fix this? This is the great opportunity.
Oh, I'm so glad you asked. This is a topic I'm truly passionate about. When I was in the Air Force, I was lucky enough to fly some really exquisite airplanes. I get to fly F-22, things like that. That represents like the pinnacle of the United States' defense technology posture from about 1970 to today, really, which is that we are going to solve problems by pouring money on them and building, relatively limited numbers of really exquisite platforms. And, I believe strongly in the post-World War II Western world order. I want to see that exist. I think it's led to the greatest increase in the quality of the human condition globally of anything in all history. So, with that as the backdrop, we have adversaries who think differently. In the last 30 years, really ever since, 1990, 1991, Gulf War I, up through the War on Terror, we've kind of given a masterclass to our adversaries of how America prosecutes conflict, what technologies we use, what assumptions we made. And they had, that 30 years to sit back and say, okay, how would I counter that? And that's really what it comes down to, is that, to hold a target at risk, a weapon system has to do three things. It has to survive to get to the target. It has to be able to find the target, sensing, precision, whatever you want to call it. And then it has to have an effect on it, whether that's a large enough explosion, whether it's a non-kinetic effect, whatever. America has historically done that by building stealthier or faster systems, both of which have gotten very, very expensive to get that next increment of stealth or speed. And then because I have this really expensive platform, I put really expensive sensors on it because I can't afford that many of them. And so each one of them has to be able to find and understand the battle space on its own. And now I've spent a fortune on an airframe and a sensor. So it better carry enough weapons or enough explosive or whatever to do the job when it gets there. And that then makes the platform bigger, which makes it harder to make it stealthy and fast, which makes the platform more expensive. So I'm willing to spend more on that. And this has spiraled up to the point that we're about to field, hypersonic missiles that cost $50,000 a shot. As of 8 hours ago, right, we're about to go buy a multi-$100 million fighter. That became unsustainable. And now look at it from the adversary's point of view, right? Like China has a lot of smart engineers. They can look at some of these platforms, they can make assumptions about how stealthy it is and where those vulnerabilities are. We're a more open nation, so they can look at our budget and see estimates of how many we're going to build. We're relatively public about what platforms carry them or these things, so they can make assumptions about how many of them they're going to have to deal with at once. And again, they've had 30 years kind of uncontested to build solutions against that. Autonomy to me is a tool to open up a whole new trade space that gets back to quantity mattering. And so in each of those cases, if I have the ability to effectively coordinate a bunch of things, I can make improvements in survivability, precision, and effect without necessarily needing a human in each one of those. And I think that this is, in my mind, the clearest path to continuing to deter like global conflict and allowing the world to continue on this path to greater prosperity. And so yeah, that's a topic I'm passionate about, is just how can I do more, control more things with the same number of people.
Chris, just to go a layer deeper on this, what do you think was a turning point in this thinking about mass? Because I don't think that anybody ever said, mass doesn't matter. And so, how were the fleets sized for these sophisticated platforms? And was the surprise in underestimating the lethality and the density of the integrated air defense systems of expected opponents? Or was it the realization of the vast amount of territory that needs to be covered? And so, therefore, with these exquisite systems, you just cannot have that luxury of saturating the battlefield at that size and lethality combination? Or was it something else?
I think it's a little bit all the above, and I would challenge the question that we ever didn't think mass mattered. I mean, obviously it does, but you also it's just true that with the transition to precision weapons and then more survivable delivery platforms, like we very aggressively scaled down. I mean, we showed that it takes a lot less things to achieve a given effect on the adversary, and I think we just got a little too enamored with that concept that we went from World War II, Korea, Vietnam, the concept of sorties per target to very clearly in 1991 and on the number of targets per sortie. And it's very seductive. When it works, it works very well. But like every other tit for tat and, for thousands of years of military history, it was going to swing back the other way. And so I think we're getting there. And, this is not new. Folks have been thinking about this for a long time. Again, there have been books written about it. There were studies, war games that showed all this. Part of it was, like I said earlier on, the technology had to reach a certain point. If you'd come around 15, 20 years ago and said, man, I see a world where we're going to have literally $10 cameras with grenades strapped to them flying around Ukraine, finding Russian airplanes and vehicles on their own. There were people writing about that in science fiction, but the technology just didn't exist. Like the state of the art for computer vision just wasn't there. So some of those things had to change. And then you can tell where I'm going with this. Like the big thing has been Ukraine. I think if you told an average, I don't know this, and I don't want to put words in their mouth, but I think if you told modern industrialized nations like air defense commander that had a bunch of missile systems under their charge, or a tank battalion commander, that they were going to be excluded from the battlefields completely by a bunch of toys, $300 plastic drones, that they wouldn't have believed you. And now they can't ignore it.
In the interest of being the devil's advocate here, and to take this conversation to maybe an absurd extreme, but let's say that we had a UFO type of aircraft or system that could teleport itself wherever at any point in time and project power in a way that is unimaginable. And if you could bet the entire budget on that exquisite capability, why would you not want to do that?
Yeah, I'm not going to do a good job of engaging with this devil's advocate. I hope that's what NGAD is. I'm jealous of the guys who are going to get to fly it. And if it works, I'll be forever grateful. But, I just said there's always a cycle of tit for tat, whether it's an offensive technology, a defensive technology. It is fragile. When I started flying F-22s in 2005, you can go back and look at the articles that were released around that time. The first red flag, 100 something to 0. It wasn't my sortie, but we were joking about it in the bar at Nellis one day that like there was a mission where, eventually Raptor 1 just waits for a gap in the radio and just shouts, every F-16 in the Nellis airspace is dead. Just trust me. That was literally the biggest challenge that first couple of years, was finding enough time on the radio to call all your simulated kills. That's changed, right? Like we've reached parity both in our own training and in the adversaries. And it probably happened a little bit faster than we would have hoped. And so, yeah, if there is an invisible UFO that can just do whatever, then we should certainly keep researching those technologies and certainly keep going there. But for the money, and where I'm sitting right now, this suite of tools, right, like extending the capability of any one human by not forcing all these things to still be attached to their platform, seems like a really promising and cost-effective way to continue to address this. And the other areas, sorry, not to drag out my answer, but when you're talking about the defense application specifically, like the perception and deterrent effect is almost as important. And so think of things not just in how stealthy are they, how far can they fly, how many weapons can they carry, but what impact does it have on an adversary's decision calculus? And so if I go build the UFO and they say, okay, this is invisible, it can go into hyperspace and it can hold any target at risk, That's certainly going to get their attention. The B2 did that. F-22, F-35 did that. And then they got to work countering it. Distributing that same strategic effect over thousands or hundreds of thousands of individual things, it just presents more uncertainty to the adversary. It's more geographic areas they have to cover. It's more types of platforms they may have to cover, things like that. And so, in general, if I had a choice between two solutions for the same amount of money that I think could solve the immediate problem, but one of them did so in a way that was more uncertain for the adversary, I think I would pick that one.
I think that latter approach also feels like a lower risk bet to make, to go with that mass and to go with the capability that's embedded in it versus making a bet on the one all powerful system that you can build very, very few of. It's not only uncertainty, but it's a lower risk path.
Right.
And if you extrapolate and you become a master of building economical, lethal mass, then the paradigm shifts even further than what we're already looking at in Ukraine. I mean, you could build autonomous systems that you could infect another country with during peacetime, and you almost have a gun to their head. I mean, it's almost like drone locusts that would be all over. There's a lot more extrapolation to this concept than what we have today.
Define air superiority over the last 10 years and over the next 10 years. What's the role of autonomy? And if you were king for a day, what would you do to change how we perceive air superiority over the next 10 years, particularly as it relates to autonomy?
That's a good question. Again, some backgrounds. I mean, I've talked about this 20, 30-year period that was kind of ushered in, or at least the world realized it started in 1991. I think we'll look back on this 20, 25 years in history as like an absolutely unprecedented and potentially unrepeated phase of human military history forever, back to sticks and rocks, right? After the fall of the Soviet Union and with, all of our second offset technologies, stealth, precision weapons, etc., there was a couple of decades where there was literally no point on earth that America could not conventionally affect if we wanted to. I don't know that type of unilateral dominance will ever be achieved again because of the democratization of the kind of tools that we're talking about today. Unfortunately, like an entire generation of senior military leaders and decision makers have come to believe that that level of dominance is our birthright. And what you're seeing now is the world, at least America, waking up to the point that is not guaranteed anymore. And so I grew up. I mean, a standard F-22 like mission objective that we'd write on the board and train to was like zero blue losses, 100%, sanitization of the enemy, 100% weapons on target on time, just absolutely zero quarter given on anything. And that's just not realistic anymore. And this is not unique to me. In fact, like the Merge podcast or article just 2 weeks ago, was talking about how the Air Force is explicitly discussing phased or pulsed air superiority, right? The ability to gain enough control over the battle space to achieve some other effect, prevent an amphibious landing, deploy some forces, and then come back, because we just no longer have the dominance, the logistics train, the number of platforms, et cetera, to maintain that level of dominance across the board. And that's what you're seeing now. I mean, there's a lot of compounding factors to this, but I think if you'd told US Air Force mission planners 10, 15 years ago that, roughly peer conflict would occur in Ukraine between Ukraine and Russia, and that 3 years in, there still wouldn't be clear air superiority established, that just would have been an absolute foreign concept to them. But it's obviously realistic.
And that the air superiority that was still in question was achieved through these plastic things, as you say, as opposed to what they would have imagined 15 years ago. So the next 10 years, Chris, you're king for the day. What would you do different than you think the path we're on right now? And how should autonomy play a different role than what you think the current planning is?
I think and I hope that we'll develop and deploy these as complementary technologies. The challenge in going all in on low cost autonomous mass, even though we may not understand them fully right now, it's going to have weaknesses and challenges as well. There's still going to be room for some of the traditional systems that we've built. Obviously, again, with the news today that the NGAD program is moving forward, I think they're very complementary. I think there's both an offensive and defensive side to that. Offensively, it goes without saying that if you're going to build lower cost systems and use more of them, you're going to take trades in things like range, endurance, payload capacity, et cetera. So you're shifting some of that risk to logistics concerns. Barely a year into Ukraine, you started seeing excellent articles, both from folks who were fighting, in there, as well as like the rest of us watching the lessons learned from this. It's like, okay, it's time to shoot the archer, not the arrow, because there's too many arrows. So I think that's some of the area I think you're going to see more focus on. Well, you are seeing focus through efforts like Replicator and stuff on the supply chain, the manufacturing, the logistics concerns, the command and control channels, data links, assured connectivity, cyber attack surfaces, resilience to adversarial AI, things like that. I think those are going to be the areas that we have to defend against. And we'll need to think through those things both offensively and defensively, just like everything else. How can we, protect and provide these capabilities for our forces and deny or degrade them on the adversary side? Again, we have the benefit of hindsight looking at this. I believe it was in 2014, 2015, there was a Taliban attack in Afghanistan that got onto base and threw grenades and destroyed a significant chunk of the U.S. Marine Corps' Harrier fleet in one day. They weren't shot down. All their training, all their technology was of no use. This was individual people with hand grenades. That squared is the world that we're getting ready to face going forward.
Small drones as offensive counter-air assets.
A lot more flankers have been killed by literally plywood and foam drones than have been killed by any surface-to-air missile, period.
That's crazy. Okay, so building autonomy. Let's rewind back to a team that wants to develop an autonomous system. Break down that process in whatever logical chunks you want to break out, whether this is collect data, train and develop algorithms, test them, operationalize them, or refactor this however you want. But talk about the process and where the challenges lie for each of those.
Gotcha. Again, this is how I choose to do it. It's how, at Merlin that we approach this problem. And again, it's to go back to that earlier comment that autonomy is hard for a bunch of reasons: trust, explainability, shared command and control, modularity, and certification. And so for us, the most important thing to get right, there's a variety of tools you can use for each level of the stack. But if you don't have the architecture in place, and it's an architecture that's capable of, if it's a civil application, can I deliver the artifacts that the FAA is going to require to allow me to pass the certification program? If it's a military platform, am I able to interface and interact with all these other exquisite sensors and things like that I'm probably not going to necessarily own? So in that case, can I plug into the government reference architecture, things like that? So getting that architecture correct, understanding those external touch points, that's the first thing, right? Like a definition of autonomy or an autonomous system is something that, it makes a decision, takes an action based on a perception of the world. So again, perceive, decide, act, OODA loop, sense, decide, act, all these acronyms all mean the same sort of thing. And then within that, one of the things I haven't talked about a lot is why I think modularity is so important here. And one of the things, all these military systems we've been talking about, I'm sure you've had folks on your podcast earlier who talked about just lamented how long it takes to build a new airplane, right? Especially a military platform. Software is obviously moving much quicker. And so one of the advantages of modularity is that we can, again, decouple those timelines, start to realize software benefits on a software time scale that's decoupled from the underlying hardware. So that drives the modularity. Within that, the trick to make a modular system work is you decide where to put those boundaries and what level of abstraction you're willing to accept. And every one of those decisions is a systems engineering trade. The more I'm able to tightly couple a system together, vertical integration, if you're thinking like manufacturing processes, bespoke tight integration as it gets onto an individual platform, there's at least the potential of higher performance if you do that. But what you're trading away is some of that ability to rapidly evolve your system, rapidly iterate, expand type of platforms that you can work with. So getting folks, the right interdisciplinary team together, you absolutely have to have folks who understand the operational problem, the context, and those cultural impacts, who are able to effectively communicate that user story, user experience, and requirements bidirectionally to the technical team. I spent a lot of my time, talking about and trying to teach aspects of combat aviation to engineers, and at the same time trying to teach a lot of these engineering caveats to my peers who are still in the operational community. I think that like increased understanding at that level is only going to make everything better. So you've got that team, and then these are interdisciplinary problems. In order to effectively execute here, I need folks who truly understand guidance, navigation, and control systems, fly-by-wire, core robotics. I need people who understand, various techniques, old school deterministic methods of optimization, path planning, et cetera. I need folks who are experts in the various, modern AI learning-based approaches, whether that's machine learning for perception, things like computer vision, stuff like that, whether that's tools like reinforcement learning for behavior definition, some of the modern research into the transformer-based architectures, VLMs, et cetera, that can kind of bridge some of these gaps, be able to understand where the overall community is going, what tools are going to be available, where the market's going, and be able to bring that together. And so once you've got all those ingredients, honestly, when we start a new effort, a new use case, my personal technique is just to have a couple of days of raw brainstorming, allow the team to think through like what the ultimate architecture could be if I had to solve every use case that I either know about or could imagine, and go from there. But then absolutely time box that, right? Like a team that only ever cares about building the perfect architecture and solving every potential use case will never move past that analysis step. I want them to be aware of those trade-offs, understands what the potential regrets could be in the future. And then we snap a chalk line, we come back the next morning and we start solving this particular problem, but with those things in mind. The two major areas that I focus on are, there's a certain minimum level of performance, that user requirements that's non-negotiable. And then at every step along the way, I use the absolute simplest tool for the job. So if it's fly an airplane, inner loop stability and control, we know how to do that. We've got 100 years of flight control system development behind us. I don't need to waste electricity and time like trying to train a neural network and accept all the regrets that could come with that for problems I already know how to solve. Pick the right tool for the job and then go from there. And in general, given the domain, simpler is going to be the tiebreaker. So you develop the architecture, you decide what your abstractions are going to be. There's a variety of techniques in there, but it can be as simple as like I have some decision or planning layer and then some control layer that actually flies the airplane or steers the sensor or something. What's the right level of abstraction between those? If I'm capable of just passing a flight plan, waypoints, and maybe buying an off-the-shelf autopilot to execute that, there could be some real benefits there, right? Like I can either buy a certified autopilot or I can certify it. I can very deterministically check that flight plan against, hey, am I flying over a country's border I'm not allowed to fly over? Am I flying into the ground? All those things. But at the same time, you can imagine, and with your background, how would you describe an air-to-air engagement, defensive maneuver, et cetera, in terms of waypoints? That's obviously missing out a whole lot of context of high-performance maneuvering and things like that. So, deciding what that abstraction is going to be. Am I able to pass a flight plan? Or do I need to, no kidding, be talking in terms of G and roll rate, stick and throttle in there? Find the right level of abstraction, build the right guards around it, and then go on. The last thing that I'm a real big fan of is because the architecture is so important, achieving some sort of 80% solution, even if the performance isn't where it is, but just, in engineering terms, like getting water through pipes and starting to validate some of those assumptions that you made about architecture and abstraction. You want to try and find all the problems in your thinking as early as possible in the process. And this isn't cosmic, right? Like, fail fast, fail often is, a mantra in this space. So it's not like it's new, but there's always an art to getting it done right.
You mentioned government reference architectures before. Are the autonomy architectures that you were just talking about, are those redesigned with every effort? Or are those architectures well-defined, well understood, and well accepted? Let's just focus on the DoD community.
The short answer to all of your questions is no, right? Like we're still at the leading edge of this industry, of these tools. There's not a fielded CCA, degrees of autonomy and actual fielded operational systems are not really out there. I think you have strong but healthy disagreement about almost every aspect of what you just talked about. For the commercial and market aspects, the market model, like the way companies are going to realize revenue, developing into a system that is heavily biased towards a government-owned platform is still uncertain. How do you appropriately incentivize enough smart engineers, enough private capital to get into a space that is not necessarily going to reach the kind of scale that you see, in civilian electronics or software apps or things like that. I think that's an open question. What degree of portability and modularity is acceptable? A lot of folks use the phrase app store. I want the iOS or the Android, and then, somebody can sell me a dogfighting app or a surveillance app or things like that. The big question is who gets to be Apple in that case, because they're the ones really making money out of this, not necessarily any individual app provider. And then also, is that model sufficient, right? Or does there need to be some prime, somebody at the end of the day who can wrap their arms around this and say, I am certain that this particular collection of software tools, platform, et cetera, is able to do the mission you need it to do? Is the government capable of being that lead integrator and that mission validator? Or are there like technical skills, longevity, et cetera, that are going to drive that to be in the private market? How would you stop that participant from owning and adjusting the reference architecture in a way that would, perhaps inhibit competition in the future? I think these are all open questions. I'll end that on an optimistic note, though, which is that knowing a lot of the participants in the space, both on the government and industry side, I think there's broad agreement that solving these problems is important, that continuing to enable the deployment of these technologies in a way that's responsive to the government and the defense market demand, that doesn't close the door on the next, bright young person with a good idea. Everybody stands where they sit. Companies are trying to secure their competitive position. The government's trying to get the best deal for their money. But at the end of the day, what you've got are a bunch of great Americans trying to solve common problems. And despite the friction and uncertainty, I am optimistic to see the broader team come together.
And despite the benefits and the motivation behind modular open system architectures and the separation of flight autonomy and mission autonomy and thinking about avoiding vendor lock, moving at the speed of software without impacting airworthiness, all of these things aside, what do you see as an unintended pathology of this concept? Maybe we can address this in the context of the CCA or any other more generalized concept.
I actually heard a government representative at one of these sessions say, hey, like, if you want to go fast, go alone, but if you want to go far, go together. And, I think that sums it up really well. They're trying to bridge that gap. The first challenge, the first pathology to overcome is that modularity, open design, it does not make the first article cheaper, faster, or better. What you're doing is you're attempting to preserve a competitive landscape in the future so that you don't get stuck with a non-optimal solution when that winning contractor's A team goes off to win the next big program and you're left with whatever they feel like giving you. And so I think that's there's a pretty good realization that that's the problem we're trying to solve. The pathology we're trying to avoid is paralysis by analysis and giving everybody a veto. You know what I mean? One of the challenges with any sort of consortium or committee-based process is that everybody can say no. Nobody's really sure who can say yes, and how you actually move forward and establish things there. I think it takes strong leadership from government, and it takes strong agreement from industry to follow that leadership. And, knock on wood, so far so good.
There's a lot of buzz in the robotics domain about advances in visual language models and visual language action models. To what extent do you think that applies to what we're talking about?
Honestly, I'm still trying to decide that myself. I'm enough of an enthusiast that I'm just incredibly excited about what I've seen honestly within just the last few months. And despite being pretty well entrenched in this industry, the pace, and I know these are all selected demos, right? Like nobody puts out a video, well, unless they're trying to make a point themselves, like nobody puts out a video of all the things that didn't work. But I think the pace of acceleration in the last year or so has been absolutely eye-watering. It absolutely exceeds what I would have predicted a few years back. And to be honest, I'm excited to see where these tools go. That said, today at least, I still feel really strongly that the concepts of the modular, hybrid, and hierarchical architecture still, solve all those problems that I've been talking about. I think what we're starting to realize, though, is that you may be able to use very general purpose tools at each level of your hybrid and hierarchical system. There was an incredible paper out of the Waymo guys last fall, and they use, like their robotaxis are driving a hybrid and hierarchical system that works similar to how I said earlier, that it has perception, modeling, trajectory generation, trajectory following with various safety systems layered on it. They ran an experiment where they wanted to see, I believe they used a Gemini network. I'm not sure exactly which tool, but they wanted to see if one of these large transformer-based models could really tackle the whole problem. And it was not perfect, but it was positive research. But what I thought was interesting was they still, even though they were using the same tool, they were using it in a modular fashion, right? They asked the network, hey, make sense of these camera views and build me a world model. And then they asked the network, where do you think these vulnerable road users will be, over this time horizon? And then they asked the network, what trajectory do you think I should follow? And went through that. So even though they were using the same tool at each step, they were still invoking it in a modular fashion. And then I just think that's an incredibly exciting field going forward.
What about the data challenge in building autonomous systems that fly? Can you shine some light on to what extent you can rely on synthetic data? What is the state of the art in terms of quality of that data that is acquired in simulations versus having to go out and collect real world data that's highly annotated or otherwise much higher quality than what you can get out of some of these simulation tools?
Yeah, I think this is similar to your questions about the role of the architecture, like the maturity and the acceptance, in that, for this particular application, like if I were to use CCA, we're still building the first one, right? We're still building V1. And so what the pipeline looks like to collect data from fielded platforms, get that back, label it, annotate it, clean it, augment it with simulation tools, and put that back into training. To the best of my knowledge, nobody has that yet. That is the next step out there. So it's important to point that out. The Air Force invested heavily for a couple of years now in starting to build aspects of that pipeline, really centered around Eglin Air Force Base. The ACC's Experimental Operational Unit, the EOU, is going to be the first user of CCAs. And that's their charter, right, is to get these things out there, start training with them, collect this data and go back. But, to some of your audience who aren't deep into AI, it is difficult to imagine the scale of data required before you can start to use AI to solve these problems. At Epicai, we used less reinforcement learning than the other teams on that DARPA Alpha Dogfight and ACE programs. But I can confidently say that our agents flew more simulated dogfighting in a weekend than all humans have ever flown real dogfights since the invention of the airplane. And we were doing less than everybody else. Like, that is the scale of data required in order to do this. And so the tools for how you collect something in real life and then how you come back and augment that with sufficient quality of simulated data. So it's not that your collected data from real life is turned straight into your training pipeline. It's that you use that data to improve the quality of your simulations and your simulated data set, and then you train on that, and then you have a validation step on the back end. And while this is not my industry, I think you see that in practice with the autonomous vehicle companies, again, whether it's Waymo or Tesla or whatever. Yeah, every Tesla out there is sending clips back when it sees something it doesn't understand, but that's not trained on directly, right? That goes to their infrastructure. They build millions of permutations of that and then put, in sim and then put that into the training system.
Yeah, that's interesting. I was recently speaking with a robotics researcher, and we started talking about synthetic data and some of the more well-known simulations that exist out there. And this person was quite bearish on the quality of that data. And one of the things that this person mentioned was that in classical robotics, you could split the simulation problem into perception piece and the motion control system piece. And you didn't really require high quality simulations for evaluating and testing some of these models. But once you start breaking up that barrier between the two silos and start talking about things such as a vision language action model, then you need to start simulating everything from the pixel to the control system in a single simulated environment. And that is way too immature at this point to represent the real world. Have you come across this problem, or is that maybe specific to generalizable robotics?
A lot of the early architectural features that I talked about, the way we chose to address the problem, all the way back at Alpha Dogfight, was specifically a response and acknowledgement to this. And this was before the current deployment of the VLMs and the incredible video that Boston Dynamics released, 2 days ago, showing Atlas doing backflips and stuff. So again, I want to acknowledge that, it's amazing. I mean, when you throw like, I don't even know, 10 to the what exponent, number of computational cycles and hundreds of billions of dollars of investment into space. obviously, breakthroughs start occurring. That's just a given. But, that was exactly it. That's why I so strongly advocate breaking up these systems and using traditional tools where they're sufficient, because the idea, especially in a defense application, right, where the scale is never going to be the same as some of these other markets, driving your simulation to the point that you can have confidence in that end-to-end answer and that it will survive simulation to real transition. I don't have that confidence. I don't think it exists yet. And then again, for defense specifically, you have two other real key challenges. And I'll just talk perception for a moment, although your point about the end-to-end problem stands. The first is that if I want to go, train a system, use computer vision to sort packages in an Amazon warehouse, like that is I have access to that, right? I may be able to control the lighting. It's relatively straightforward to gather the data or start to simulate the data that I need in order to train that. It is significantly more difficult to do that on, pictures of an SA-22 missile system in a deployed environment. Strangely enough, those type of systems don't necessarily appreciate you coming up and taking a bunch of pictures from every angle. So you've got that for one. You're going to be dealing with much sparser data. It just doesn't exist in the world. And then you're going to be dealing with an adversary, right, that is going to attempt on as fast a cycle as they can to, change that problem for you, make that problem harder. Everything from basic camouflage and concealment all the way up to advanced adversarial AI attacks. And all those things are kind of hitting at that core assumption that you're going to be able to build the perfect sim and train the perfect behaviors in it. So you absolutely have to be cognizant of that problem and use all these other techniques and design architectures that are resilient to it.
If we end up going down the path where we need real world data, does that mean that incumbents necessarily have an advantage over any startup that's trying to innovate in this space? Because in automotive, what worked was you either had the Tesla model where you fielded cars and then you collected data and were able to use that for training your AI models, or you had a Mobileye model. But in an aerial application, accumulating that real world data is very expensive. And so, how does a startup do that as opposed to an incumbent OEM or operator?
I think there's a couple answers to that go beyond just a little bit of the data question. But, just on the data side, my general opinion of what we've seen in Ukraine and similar areas is that it's not like there's any one vision model that's ruling the world. Instead, what you see are the differentiator is kind of the pace at which you can make these updates. Is your training system able to take a single snapshot from a system that came back and then, amplify, augment that data and improve your models the next day? And so, it's one of those areas where I think there's a long tail. There's plenty of room at the bottom to go out and solve individual problems. The second thing is that in the defense ecosystem, right, that you have a couple orders of magnitude of scale that are all still within the startup realm, right? Pick just of well-known spaces, right? Like even Shield AI and Anduril, which a lot of people use in the same voice, are roughly an order of magnitude apart in terms of resources, scope, deployed reach, et cetera. Obviously, Palantir up at another level there, and then you've got the primes off to the side. And so, not everybody's going to be good at everything. And I think what we're seeing now, in Palantir and Anduril, I think are excellent examples of this, is that the type of problems that your traditional aerospace primes were built and organized to solve are not necessarily the problems that apply to these autonomous systems. You want to be able to attract different people, use different tools, and potentially have different go-to-market models. And so, I'm generally optimistic, again, that like the Western world and the way we build and form companies will continue to adapt to all those different areas.
You were talking about the recent fighter contract that was awarded just a couple hours ago. Is there anything you could talk about that to educate our audience on what you think they should know about it that would be of interest?
I don't think there's much I can add compared to what's out there. Is that, I obviously think autonomy is going to open up new trade space. It's going to continue to add uncertainty to the adversaries and augment our capabilities. But I'm not so naive as to think that, autonomous affordable mass is not going to have its own weaknesses. And so, this is a bet similar to what the Air Force just said, at AFA, right? That they war gamed this out a lot of ways. And while there are a lot of answers to these problems, they liked the outcomes better when NGAD, the next generation air dominance platform, was part of the system. And so, I think we're going to have all the same challenges that the F-22 and F-35 program did. I think in order for this to move forward, there going to try and build a lot of cool new technologies that are going to all come together in a very complicated system. I think controlling cost and balancing that against when we can actually get these things out in the field is going to be important. But from everything I've read and heard about it, it sounds like it's going to be a really exquisite set of capabilities, and a little bit jealous of my peers who are going to get to fly it someday. Actually, a lot bit jealous.
Nice. Listen, people can't see you. We can. And behind you is a racing horse. Why is that behind you in your office? Do you mind?
So, like I said, I just moved a couple of months ago and haven't unpacked my office. Historically, and probably the last time I talked to Peter and Luca, this was all my Air Force memorabilia and stuff. But it just so happened that one of the first things I've unpacked when I got here was that photo. My wife used to competitively train and compete in equestrian. And so in what's an otherwise bare room, I've got a picture of her running an upper level cross country event. Just, one thing it speaks to me, and it's one of the things my wife and I talk about a lot, is that when she was riding upper level horses, in flying airplanes, there's just something amazing about, being able to exceed the limits of what a human can do. And for Amy, it's partnering with another living creature to, go jump over these 8-foot obstacles and stuff like that. For me, it was getting to fly airplanes in a previous life, but it's something we both talk about sometimes.
Good. All right. Well, Chris, this episode has been in the making for a long time. So glad that we were finally able to coordinate it. Thank you very much for your time and for sharing your thoughts. It was a treat.
Yeah, I really enjoyed it. I look forward to talking again.
All right, that's a wrap for today. Thank you for listening to the Vertical Space podcast. Reach out if there are topics that you would like us to discuss, and goodbye until the next episode. Unless mentioned, this podcast is in no way endorsing or promoting any person and or company mentioned, and all opinions within the podcast are solely that of the presenters. The Vertical Space makes no guarantees, warranty, or representation of any information given in this podcast. Any information given is for informational purposes and should be used at your own risk. This podcast is for general, educational, and entertainment purposes only.